Okay, now we come to the AC network analysis. So earlier we saw the network with only DC circuit, right? Earlier with DC circuit. So we saw with many techniques, right? For example, nodal analysis, mesh analysis. We use superposition. We can transform to Thevenin and Norton equivalent circuit, right? Thevenin and Norton equivalent circuit, on and so on. But if we face the circuit with AC means alternating current circuit, right? Alternating current, right? It means AC. DC is direct current, right? Direct current. DC means direct current, no change. DC means, for example, battery. Battery is DC circuit. Alternating circuit is the electrical system in your home, right? In the building, in your dormitory is the AC circuit, right? The AC circuit will be come like this. With the voltage change at all the time. The voltage is changing at all the time. But when we compute this circuit, we have some techniques to solve this circuit. Do not to solve it in complex term, right? If you solve this circuit, it may be difficult, right? It will be in the term of Vmax here, Vm here, into sine wave, right? Sine omega t here. Omega means 2 pi f here, and this is a complex term, right? But we can solve by using the RMS value as the or phasor techniques. We will use the phasor technique. What mean 22? For example, in Thailand, what is 22 volt? 50 hertz. Is 22 volt mean the wave of the voltage come with 22 multiplied with square root 2 here. This the peak is here, and 50 cycle. This is one cycle, right? 50 cycle per 1 second. So it's changing very fast. It's 50 cycles per 1 second. 50 hertz here. So this is we call AC system. For example, in some country, maybe 110 volt, right? So what is the voltage in here? We have Thai student and Philippine student, right? For what is the voltage value in your home in Philippines? Anyone can give me this information? Any Filipino student? Are you are not sure? Or you're not sure? I don't know, right? But in Japan it's 110. In Thailand it's 220 volt, right? Okay, so this part we talk about the AC network analysis and AC power in this chapter and this chapter, but not the whole chapter, right? I select some basic concept for you, right? Because at least you should know about how to solve the AC network analysis and how to compute the power in AC circuit. So what in terms of watt, and reactive power in terms of var, for example, in terms of VA like this, and what is complex power and the three-phase power. So what does the power in the factory, in the large building, usually we use three-phase electrical system like this. Okay, so here the content in chapter 4 is AC network analysis. So first, to solve the AC network analysis, we need to understand about the energy storage element. Energy storage element means capacitor and inductor. Instead of resistor, we have resistor as a passive element. It will dispatch power, but for capacitor and inductor, it's just solid element. If the voltage across is not changed or the current is not changed, if you not act everything, it's charge and discharge energy only. And in the case of storage, even if you have the time to charge and discharge, we can compute this characteristic in time dependent form right here, and it will act to time dependent signal source here, right? And I will show you how to solve this kind of circuit, right? With this energy storage element, and then I will introduce you how to compute AC circuit using phasor techniques, phasor solution, which will help us to solve the AC circuit easier by using phasor techniques. Okay, I will just introduce you about the capacitor and inductor. Okay, and these two type of element is the storage element. This is we can call energy storage element, or this is a dynamic circuit the element. To distinct mechanism of energy storage exists in electric circuit: capacitance and inductance, both for which lead to the storage of energy in the electromagnetic field. Right here, this is the capacitor. Yes, it's used in many equipment and device, and it is the phenomenon in between two plates, right? The charge in between two plates, and it stores the energy in terms of charge here. In terms of charge, when it fully charged, it becomes open circuit here. If the voltage is not changed and it's charged fully, it just act as an open circuit, right? But for the inductor, is the coil. It's a coil, a kind of coil. It depends on the design, how many number of turn, and what is the material used, right here. So it stores the energy in terms of magnetic, right? In magnetic here, magnetic coil, and if it's stored fully energy storage, it's become short circuit. Yeah, it's become a short circuit. If we charge, if fully charged coil is become short circuit. Okay. Yeah. Then let's see the ideal capacitor here. The capacitor will act to the voltage across it in the relation as if the voltage is changed, the rate of change of the voltage, right, is the current. The current is the constant value into the rate of change of the voltage here. This is the property of the capacitance here, and the C value is the capacitance in terms of the unit is farads, right? Farads, or microfarads or picofarads here, and so on. So if the voltage across the capacitance is changed in the rate of dV by dt, right? So if the voltage is not changed, what happened? If the voltage is not changed, it means that if you put DC voltage in here, right? If the voltage is not changed, there is no current, right? Because dV by dt is 0. It means the current is 0. So the capacitor will act as open circuit, right, for DC. So if the voltage is changed, maybe you make some switching or you put the AC circuit here, it will the current will flow in this relation, here, right? Yeah. So with this relation, we can write down the the voltage in form of current. So VC would be 1 by C integrated from negative infinity into t to the time of current IT here. Okay, from after long time, long time back, right? And into the time we consider here. Okay. And then the constant value that we get from the integration, this is the differential equation problem, right? We integrate for VC in terms of IC here, right? Then we get V at V0 is VT at T equal to T0 here, and is 1 by C integrate from negative infinity into T0 IC T palm dt palm here, right? We get this value here, and then after that we can have the value at any t by this equation. Okay, and then if we connect the capacitance in series, then finally we will get the total capacitance with this equation. Okay, but if we connect in parallel, we'll get with this equation, right? It's sum together with this equation. I think you're familiar with this relation. Okay, let's see some relation between voltage and current across the capacitor. Okay, for example, if the voltage here, right, we apply the voltage to the capacitance or capacitor with this function, right? When the time from 0 to 6 microseconds, the voltage increase from 0 to 5, and then after 5 it's become constant. What happened to the current flow, right? When we start to apply the voltage, here we have dV by dt, right? The voltage is changed, so I equal to C dV by dt. If the voltage change is high, the current value is high, right? So the rate of change is lower, right? What is this? dV by dt is the slope, right? Slope of this graph, right, is become flatten and become zero graph. When it becomes zero, no current flow at all, right? So the current start with a high value and it's decreased, and then it becomes zero, right? So after long time, the voltage, if the voltage is not changed, it's become open circuit, right? No current flow in this case, right? This is just to give you some characteristic here, right? And the function of this graph can plot from this function, right? The graph is plot from this function. Okay, just to give you some idea. So don't worry about the equation. And then if the voltage change like this is constant voltage, right? Even the voltage is there, it's not zero, but it's not change. It's not change means there is no current flow because this is zero, right? If the voltage is changed, here this is slope, right? dV by dt, this slope, the current is there, right? It's the slope of this graph, the current is there. When the voltage become constant, the current is zero, like this. Okay, sorry. Okay, then let's see another example. If we know the current is there, right? The current is 0 and 10 and then 0 again, right? It means that if the current is 0, no voltage at all, right? We can use this relation, right? Integrate current. So the voltage is the integration of this value. So it show the slope of this graph also here. Okay. So this is the property of the capacitance. So the voltage change, the current is there. The voltage constant, no current flow, right? Okay, here. And this is the capacitance value of the capacitor of different type of capacitor. It depends on it's made from mica, ceramic, or mylar, or paper, or electrolytic. Okay. And the energy stored in the capacitor can be computed by this equation, right? 1 over 2 CV square, right? The voltage across square, and depend on the capacitance value. So, and for the inductor is will have the voltage across is only when the current is changed here. This is the opposite relation, right? And is will act to the voltage by this relation. The voltage across the inductor is L. L is the inductance in Henry, right? In Henry, the unit of inductance is Henry. And if we have di by dt, if there is the rate of change of current, the voltage is there. If the current is constant, no voltage across, it means short circuit, right? It's become short circuit. If the current is constant, it's just a short circuit. But if the current is changed, the voltage is there. The voltage is there. Just similar to the capacitance, but in opposite relation, right? In this case, here, right? Similar, we can compute the current by integrate the voltage form, right? And we get the similar equation in for inductance here. And if we add the inductance, we connect the inductance in series connection. We sum it together, but in parallel, we use this equation similar to resistance here. Okay. So this part I go a bit fast, but just give you the idea, and I would like to start how to compute the AC circuit for you. It's better. Okay. I think you have some idea about C and L, right? So C, capacitance, and inductance. Okay. So let's see this example, right? If you have the current flow in this character, right? 0 milliamp for t less than 1 millisecond. 1 millisecond here, 1 millisecond, 0 milliamp, no current at all, right? But in this form, from 1 to 5, from 1 millisecond to 5 millisecond. I don't know, this is maybe this is straight line, right? This is T, right? And this is current IL. This may be straight line, something like this, I don't know. And it's become constant again during 5 to 9, like this, 0.1 milliamp. And then it's become negative slope, right? It come back like this, and then maybe current flow like this, I don't know. Yes, the current flow like this, right? Here, from this value. And what is the voltage here? If the current flow like this, is the voltage is the rate of change of current, right, into one constant value L here, right? So the voltage may be like this. If the current is not changed, no voltage, right? If the current change, right, with the rate of this slope, and it will be here, right? The slope multiplied with the inductance value, and the current not change, the voltage is 0, right? And the slope is negative, the voltage is negative, right? And then if the current is not changed, the voltage is 0 also. So this is the relation between voltage and current across the coil or the inductor. Okay. Okay, let's see this value. This the property. If the current constant, no voltage, right? If the current decrease, it means slope is negative, the voltage is negative here, right? And if the current constant, the voltage is 0, no voltage across here, right? It's become short circuit. Okay, like this here. And this is another property, another example of the inductor, right? If the voltage like this, what is the current here, right? If the voltage is 0, the current is 0, right? If the voltage is negative, the current is you have negative slope, right? And this 0 is to have constant current. Constant current is 0 voltage, like this. Okay. And the energy storage in the inductor can be computed by this value here, 1 by 2 Li square for energy storage in an inductor. Okay. For example, if you have the ignition coil of the car, you have L and I. The energy storage is 1 by 2 Li square. Here, we can compute this energy of the coil if we know the current flow and the inductance of the element. Okay. Okay, I think I will stop here, and next time I will talk about the time dependent signal or AC signal. Time dependent, in this case you have the periodic function. This is for AC source, like this. It's in time domain, right? It's not constant, it's not just Vs, and it's constant. Here is vary as a function of time, right? And we will talk about this topic in next lecture. I start from this, and then we will go to some AC phasor techniques and how to compute the circuit with AC current, like this. And three-phase circuit is there. This is three-phase circuit, and then some thumb rule for you to compute the power of three-phase circuit, and this the next homework will be there. I think I will stop here. Then I stop my record.